Hi, my name is Thomas from Flex Optics. Put that down there. I'm the co-founder and also the CTO of Flex Optics. Formerly, I was leading the software development within Flex Optics, and today it's more like I'm in the transceiver technology, what is capable and doable with transceivers, but also in the support, and I personally call it support with no levels and no bullshit. Just get straight knowledge about the technology, what you can do to build your network, and that's basically the presentation today about it. It is a longer presentation, and I'm gonna skip the theory part, which covers basically nice ice, trying me to play ice hockey, and I want to stop with that beast because that's the end of the theory part when it comes to the 400 gig transceiver technology, which I want to introduce now is the next generation. We do have already in place 100 gig, what Peter from NIXCZ already mentioned. 100 gig is mature, it's there. We do have interconnections on the 100 gig, but the next evolution on technology will be 400 gig, and that's mainly the talk about it, and especially a hands-on, what is practical for you in the network environment. The end of the theory part of my talk, which is now, is that acronym PAM4, which stands for 4-level pulse amplitude modulation. And the key point there is, when for the following slides, is keep in mind on the same frequency we can do with PAM4, we can encode or modulate 2 bits instead of 1, and that's a really important thing to understand the ongoing thing now. So hands-on about 400 gig. We open up a transceiver, and we do have always in a transceiver 2 sides. We got an electrical side over there, and we got the optical side over there. Starting with the electrical one, it's basically the bare PCB. You place in an ASIC or some IC chips, which take the electrical signal from your switch and do some magic, and then get it over to the optical side. So what about I got the headline PAM4, so that's somehow the symbol for PAM4, which I defined it, makes 400 gig. So PAM4 is a critical component in the modulation in a transceiver to enable 400 gig. And why? That's quite simple to understand when you understand 100 gig. So in 100 gig, we did 4 times 25 gigabits, and those gigabits had a frequency of 25 gigahertz. Pretty simple. So we encoded or modulated on a single with 25 gigahertz, 1 bit in each beam. Now for 400 gig, we need something more fancy, and when we use PAM4, we can double the density just on the signal up to 56 gigabits because we modulate 2 bits in there. Double the data rate to 56 gigabit, and we would have 4 lanes, would end up 200 gigabit, but we want to reach 400 gigabit, so then it's pretty simple math. We increase the amount of lanes, and that's what we see here. So we got 8 lanes on the electrical side, talking to our host, and also from our host to our transceivers, doing 56 gigabit. Now coming over to the optical side, this will be the first generation, also having 8 lanes running on PAM4 with 56 gigabit, basically 8 lasers on a speed of 25 gigahertz, modulated with PAM4, getting out 56 gigabit for each laser. I don't mind now, or don't discuss if it's a multi-mode or single-mode transmission. At the end of this day, it's the same theory behind it. Later on, with the time down the road, 2019, 2020, there will be an improvement. The electrical side won't change. It will stay still the same. There will be a new component in there, a gearbox. So what does this gearbox do? It takes those 8 lanes, combines it to 4 lanes. And what it does, it drives an optical engine which can do 4 lanes with 112 gigabit. Still PAM4 modulation, but with a way higher speed on the optical components. Now, the question is, why can't we just do that on the electrical side and get rid of that gearbox, remove that chip, and increase the speed on the electrical side? And that's a serious issue when it comes to efficient manner to produce a PCB on high frequency signals. So when you want to increase the frequency, you have to reduce the length of your lanes, or even change the substrate, the material itself, and that's going to be really costly. and that's something what we want to avoid. So a chip is cheaper than a costly substrate material of your PCB. In terms of applications, sorry, no, missed that one. So in terms of form factors, because that's something what you will hold on later on in your hands, and you're quite familiar already with the SFPs, those tiny pluggables, look like those ones, or even like QSFP28, the latest 100 gig technology, which is up there. There will be 400 gig solutions called the QSFP-DD and also the OSFP. So what is so special about QSFP-DD? The DD stands for double density, and it has some really nice things in there. You see those connectors back here. It has two connector rows connecting the transceiver to my super fast switch. Now, having a QSFP-DD cage, it can hold a QSFP28, the one up there, in that same cage. So the cage is backwards compatible. So in a 400 gig switch, you are able to run a 100 gig optic. And physically it will fit in there. A QSFP28 you can plug into a QSFP-DD cage. For the OSFP, that's something different. It's a new form factor. It's bigger. And it also does 400 gig, but it has some interesting components in there, which I will show later on. It has an integrated heatsink, and that's really important for the power dissipation. And for sure, the sizing is bigger, so the sizes I'm showing here, it's proportional, so the OSFP is way bigger than the QSFP-DD. Why do I mention the sizes? The sizes within the switch, I think you don't care, but as a network operator and someone who has set up a rack already, the size outside of my switch, which is here, the 20 millimeter, is something really important. And looking backwards now, since the introduction of QSFP Plus, 40 gig technology, or 100 gig for QSFP28, I got quite a lot of people asking me, hey, this portion out there of the switch is getting bigger and longer, and I'm getting really hassled closing my rack doors in the future because the transceivers are coming out way more out, and I don't have enough space any longer. The bad news is it won't change. It's even defined by standard or by the agreement of the vendors. We can have 20 millimeters out of our rack unit of our switch. So keep in mind, you need at least a 20 millimeters for the transceiver, and not taking the plug and the bend radius in consideration. So taking 20 millimeters just for the transceivers, at least 50 millimeters for your fiber optic plugs, plus maybe a little bit bend radius for your fiber optic patch cable. This would be helpful to getting the light through the patch cord. Will end up you need at least 100 millimeter space from the first rack unit to your front door. Not because only of the cabling, but also later on, what we will see at the end about the power dissipation, you need that, I'm pretty sure, to get rid of that heat, which is generated by the entire system. Now, what kind of applications are doable? On the from your side, it's the left, yeah. On the left side, we do have again a 400 gig switch, and I don't mind if it's QSFP-DD or OSFP. They can provide the same type of applications, either on SR, like on multi-mode, or even on LR technology for single mode. I don't mind, so I put both of them in that switch. I'm pretty sure the Windows won't build such a kind of switch. They either stick to QSFP-DD or OSFP as a form factor. But from the application point of view, it is interesting how you can connect later on legacy 100 gig gear, which is already there up there, the QSFP28. That's doable connecting to a 400 gig transceiver when we are at the stage enabling 112 gig on the optical layer. So this QSFP-DD or OSFP can do 4 times 112 gig, end up at 400 gig, and you can fan it out to all kind of even new 100 gig form factors. So the QSFP28, it's already there, and we will get a micro QSFP and even a SFP56DD, and even what you can later on have as a 100 gig one. For sure, it's also doable interconnecting 400 gig QSFP-DD directly with OSFP, for example, but that's obvious. Finally, on the plug side, that's I was impressed already when 40 gig transceivers were introduced. The MPO was shown to the audience, and up there, like MPO 12. And MPO had already some hassles when it came to polarity. So previously there were 2 fibers on an SC or LC plug, and suddenly with the MPO we had 8 fibers. Now on 400 gig technology we do have 8 lanes, and for TX and RX in total we need 16 lanes. So yes, there will be a new MPO, MPO 16, and lucky us, there is also a keying up there. This, I have to put it like this. The keying up there will avoid that we're gonna plug in an MPO 16 into a MPO 12 slot, for example. On the single mode side, that's a dual LC, pretty straightforward. There will also be a CS plug, and it's half the size of an LC, just reduce the density, or yeah. Finally, power consumption. I mentioned it already, and power consumption is you need cooling. QSFP28 currently has a power consumption or heat dissipation of around 4 till 5 watts. And for QSFP-DD and OSFP, we are reaching something around 12 or 15 watts. Why is that important? First of all, imagine you have a 1U switch having 36 400 gig ports. This will end up only for the transceiver portion, for the transceiver part, around 500 watts just for the transceivers. Not taking in consideration the power supply, the ASIC inside the CPU, etc. So I'm pretty sure there will be 1U switches out there reaching almost 1 kilowatt of heat dissipation on 1U. That's quite a lot of stuff. Thinking about your rack having 40 or 42 units in there, that's a lot of heat dissipation. So the 100 millimeters in front to the front door are, I think, pretty important. It's going to be a big heater. For the people deciding the form factors, the OSFP currently has an advantage because of that integrated heatsink. It's easier for them to get rid of that heat, and also of the size for sure. The QSFP-DD working group, they want to reach the 15 watts. They already showed it at the beginning of the year that they are doable to do it in the lab, and it's also their goal. Why is it so important? Because they have learned from the 100 gig. In 100 gig, we are somehow in the lag of long distance, like beyond 10 kilometers transceivers, talking about DWDM or even coherent technology. Yes, there are solutions when you're thinking about CFP, but I don't want to mention that form factor any longer. For 400 gig, these working group have in mind we want to also enable coherent DWDM technology within QSFP-DD or OSFP, and that's the reason, or one of the reasons, having that much heat dissipation, or able to have that much heat dissipation. If you're gonna ask me who is gonna be the winner, that's a really tough question, but I see the majority of the vendors building host systems jumping onto the QSFP-DD, and not only because of the backwards compatibility to QSFP28, but it's from the design perspective an interesting form factor. And when are they going to be available? The first lab environments I have seen already, they are working on it. So I think we see the first system in 2018. Don't nail me down if it's going to be in summer or in winter time, but the first 400 gig systems will be around, even with the OSFP or QSFP-DD form factor. And that's also where we also take care that the transceiver is made compatible and also working in that host system. So we have done that with 100 gig transceivers already, like thinking about ER4 technology, going beyond 25 kilometers, enabling that in a 100 gig switch, which is only capable to run LR4, and therefore we developed the Flexbox. And yeah, that's basically it. I'm finished with my talk. And if you're interested in the theory part later on, looking at the fancy eye, let me know. I'm here and happy to talk about it. Thank you very much.